All right, so I want to take a little time to explain the circuitry that I use to drive relays in the McGrath Mini amplifier and all my other amplifier circuits. It's a little complicated and convoluted, but I think I have good reasons for all the design decisions that it embodies. So we're going to open up the nice manual that I include with all the amplifiers that I ship, because I always have schematics in the back. We're going to take a look at the schematics here for the McGrath Mini. First thing to note is that I divide the relays in the circuitry between the coils and the driving circuitry and then the switching circuitry. So here you can see the switching portion of one of the relays. It just looks like a DPD switch, except it's labeled K. That one's K2 there, not the mountain. But anyway, so the switching portion of the relays is distributed into the circuitry where it takes effect, but then the actual drive circuitry, which is what I want to talk about today, is on this other page here, somewhere in there. Right back here in the relay control section. And so I guess the question is, why is my relay circuit so complicated? And the reason is essentially that I don't switch the relay current directly with the foot switch. I think that's a bad practice to switch relays with any kind of mechanical switch, because being an inductive load, they cause arcing on the switch contacts when they switch on and off, and so it's will ultimately reduce the life of switches, and it's just not a reliable way to do it. So the relays are switched by these switching transistors, NPN transistors. I've spec'd 2N2222s here, but in other cases I've used 2N3904s. They're basically interchangeable for this application. The 3904s are not as powerful as the 2222s. They can switch less total current, but in either case it's more than adequate to switch these little dip type relays that I use. So either type of transistor works here. But as you can see, I've got the NPN transistors that switch both the relay coil and the indicator LED by pulling those to ground. And then of course there's the reverse diode to short out the inductive spikes that are induced whenever a relay switches, the protection diode. So that's a standard feature of all my relay circuitry. And then down here you can see the 3 position switches that either turn the relay on all the time or off all the time, or put it into foot switch position. To turn it on, this line is actually allowed to float, and the resistor pulls the transistor base up to 5 volts and turns it on. And then to turn it off, this line would be grounded. So the off position is when this switch connects to ground, or when the foot switch circuit pulls it down to ground. The foot switch circuit is this over here, which is an LM339 comparator, which they have open collector outputs. They're either floating or pulling down to ground. So, and the threshold of the both comparator sections is set by this resistor ladder here to a voltage just a little bit below the 5 volt rail. It's not in the center. It's slightly above 4 volts, like I think 4.2 volts is what it works out to be. It's a 10K down here and a 2.2K up here, whatever that works out to be. The reason for that is that I have LEDs in the foot switch, and these are the current limiting resistors for the LEDs. And when I use a blue LED, the foot switch input varies between 5 volts when the resistor is simply pulling it up, and when the switch is on and the LED is in the circuit, then the voltage drops to the dropping voltage of the LED, which in the case of a blue LED is 3.7 volts plus whatever, plus whatever losses there might be in the cable. So it could be pretty close to 4 volts. So to be sure I can reliably discriminate between those two voltages, this comparator threshold is kept pretty high, but I don't want it too high so that it also rejects noise. So the 10K and 2.2K ladder is what I've found more or less empirically to have the right amount of noise rejection and reliable operation with any color of LED, including blue. And of course, since the current to the switch flows through these LED resistors, it's nice. There's kind of no real way to damage anything by shorting out the switch or plugging in. If you plug, this is supposed to be a 3-conductor TRS type of cable, but if you just plug a regular 2-conductor cable in, thus shorting out one of the channels, it doesn't hurt anything. It just pulls that channel down and turns on one of the channels. Channel 2, in fact, is permanently on, and you can still take control of it using the 3-way switches, so no harm is done, but you only get one operating button. Or if you just have a regular single switch, foot switch with no LED, you can go ahead and plug that right in and get control over channel 1 that way. And so it doesn't matter whether there's an LED or not. Either way, when the switch is on, it pulls the voltage below the comparator threshold and activates the foot switch circuit. And when the switch is off, the resistors pull it up to the 5 volts and the comparator deactivates. So it makes for a very reliable and versatile and simple switch input to control the relays. And that is pretty much how I do it. And anyone else who's using relay switching in an amp circuit, I would recommend pretty much doing something pretty similar, as opposed to having the foot switch actually switch the relay directly, or God forbid sending audio over the foot switch cable, which is how it used to be done in the bad old days by things like Fender amps with the reverb foot switch and stuff like that. That's really just asking for trouble. I guess it avoids some complexity, but put a relay in there and do it right, and drive the relay with a transistor, and everything will be better for you. I've noted even some modern amp manufacturers, like in the PV5150 foot switch circuit, I believe it's that amp, they have the foot switch actually directly switching relay coil current, which is kind of funny. It works fine, and it'll last probably for years without probably any kind of trouble, depending on what type of switch contacts they use. But it just sort of grates on my brain to see that type of a thing done by a professional manufacturer. A very cheap NPN transistor takes care of any worries about arcing and guarantees the switches are not under any kind of stress and will last longer and work better. So anyway, that's the explanation of why I make my circuitry like I do. Feel free to copy it. I recommend it. Boop.